org, and it includes both front end and back end. The back end, I think its functionality is similar to TensorRT LLM or VLM. And among the fully open source LLM inference engine, SGLang currently achieves the SOTA performance. Meanwhile, because it is so lightweight and for its customizable design, so many big companies and startups use it internally. Okay, and secondly, let me introduce the SGLang team. Right now, SGLang team is led by Zhang and Yineng. Yin and Liangsheng are the creator for the SGLang project. And besides them, we also have 4 team members, Brian, Ke, Chenyang, and me. Also, we have more than 100 contributors. And here, I want to give some special acknowledgement for the Zihao, Heron, Li, Han, Jerry, and Mark. Okay, here is about me. Yeah. Right now, I work at Baston, and here is the Baston blog. Before that, I work at Meituan, and from my past experience and my current experience, I work for the inference acceleration. Before that, at Meituan, I do some CTR prediction for research, for search and recommendation, and after that, do some stuff about LLM inference. And right now, I work at Baston just for the model performance team. And here are some of my contacts, my email, GitHub, LinkedIn, and Twitter. If you have any questions or do more discussion, maybe you can contact me. Okay, here let's introduce the SGLang milestone. SGLang is a project developed at last year, and at 2023 October to December, its initial motivation is to do some programming LLM paradigm. And here is the paper to illustrate that idea. And at this year, the January, we published a blog to introduce SGLang. I think it's the first framework to support LLM prefix cache. And after that, many other frameworks such as TensorRT, LLM Deploy, and VM also support it. And at February, we also published some feature like constraint decoding, and we also publish a blog. And this year at July, that's a timeline. I joined the SGLang team, and we publish a blog about the performance. Here, right now, SGLang is a fully functional LLM inference engine, and its performance is impressive. At September, we also do some feature development, some enhancement features such as DeepSeek MLA, such as the GEMM 2 attention, and also do some performance improvements. And we will release the SGLang version 0.4 coming soon, yeah, with a better performance and stability. Okay, here in this talk, I will cover 3 recent optimizations. The first one is the CPU overlap. The second one is the FlashInfer optimization and the integration. The third one is the TurboMind GEMM optimization, and we plan to integrate it. Yeah, you know, recently a lot of attention has been paid to how to remove all the CPU overhead from the inference engine, so we can make the GPU always busy. Also, previous SGLang has known for low CPU overhead, but there is still room for improvements. So we gradually refactoring our whole code base to fully remove the CPU overhead. I think this enhancement minimizes the SGLang CPU overhead from previous implementation, and is now in the latest release. I will introduce the details. Okay, let's start with the CPU overhead hiding. So this, I quoted some results from another blog post from UCSD. They analyzed the CPU overhead on various engines. There are some early version of VLM and SGLang. And as you can see, the engine can waste more than even 50% of time on CPU scheduling and just leave GPU idle. So this can be a huge waste and a huge performance bottleneck for inference engine, especially for some low latency or high throughput cases. And let's take a closer look at what the inference engine is doing when they run the inference. Basically, in a SOTA engine, we want to run continuous batching. So the scheduler needs to handle lots of things, and they are mostly CPU work. So for example, at each step, the CPU scheduler will try to receive the input and organize the next batch and feed the input to GPU. So GPU executed at batch, and then scheduler get back result, and then do some other processing and organizing the next batch. So you can see the GPU is not always busy. It has to wait the slow CPU to do a lot of stuff, to do a lot of scheduling work. To summarize, the CPU actually, the CPU actually needs to do some tons of work. So that's why it can be a bottleneck. And to summarize here, it can receive input message from the user, process results from the model worker, checks the stop conditions, runs the prefix matching, and requests a reorder, and allocates memory for the next batch. Okay, so yeah, here we show the pseudo code for the scheduling work of CPU. It receives first it receives input and then process, and then it try to get the next batch to run, allocate all the buffers and the memories for them, and then run the next batch. This is the blocking code. So it waits until the GPU finish computation and then process the results and also stream its output. So every line here is blocking. Okay, this is definitely not what we want. And yeah, this is the blocking schedule I just showed you. And ideally, we want to follow.
Sorry, Yineng, just a question. So when you say like CPU overhead, you primarily mean, right? Like, is there any other overhead you're referring to?
Sorry, can you speak again?
By overhead, do you primarily mean idle time, like basically time when the CPU is just waiting?
Yeah, I think yeah, we want to eliminate this space. Yeah, this is the GPU, this is CPU, and when CPU do some scheduler work, the GPU is not busy. It's idle.
I see. Okay. Yeah. Thank you.
Okay. Yeah. Thank you. Okay. Yeah. Let's take a closer look. Yeah. This is the blocking schedule I just showed you. And ideally, we want to fully overlap the CPU and the GPU computation. So for example, when the GPU model worker is working with the current batch, and the scheduler should be able to do the scheduling for the next batch. And then we can pipeline the CPU scheduler and the GPU worker. So we can always keep the GPU busy. Yeah, there is no space here, and can totally hide the schedule overhead of CPU. So this is what we are currently working in SGLang. And yeah, we have implemented the version of the overlap to the overlap schedule. You can check out these 3 PRs. And yeah, also if you want to use it, you can easily just use the enable overlap config to enable it. And yeah, when you want to optimize the version, you can turn the overlap option. And if you want to do some such as debug job, and I think maybe the default non-overlap version is easier for debug, is easier for develop a new feature. That's why we keep both of them. And so we can see how it works on the left side. This is the block version I just showed you. So the key idea is how to make this run batch non-blocking. So we can directly get results and try to schedule the next batch. In the overlap version, the schedule loop is quite similar, using basically all the same primitives, but we slightly reorder the loop. Here is also receive input and get next batch to run, and when you try to run the next batch, the code is non-blocking. What does that mean? We can get immediate result, but this result is a future. So we put it into a queue, and then we also process the results from last batch. So here we make the run batch non-blocking, and we can actually fully overlap the GPU computation. Here is the basic idea, but actually there exists some challenges for that. Here are 3 key implementation challenges. The first one is that how to solve the dependency. So why the normal version is blocking? Because we need to check the stop condition. If the sequence meets EOS ID or length limit, we have to remove that from the current batch and return the results. So there is a dependency in the loop which prevent overlapping. The second one is that how to share as much as code as possible for overlap and non-overlap version. So we still want to keep these 2 versions And one allows for easier debugging, another allows for extreme performance. That's why we want to share that code. The third one is how to work around with Python GRL. Python threads are kind of fake. It cannot utilize multiple cores when using multi-threads in Python. So these are the 3 key technical challenges we want to address. Okay. So the first one is the resolve the dependency. We have an idea how to resolve this. Just delay the finish condition check. We can just assume, oh, our request didn't finish, and immediately run it in the next decoding batch. We solve the dependency by paying the overhead of decoding one more useless token. And I think the overhead is small when the batch size is large. Yeah. And also the second challenge, reuse code between overlap and non-overlap version. Yeah. I think the idea here is to introduce a new tensor type called future tokens. What is future tokens? Yeah, we make this run batch code non-blocking, and it will return some Python tensor, but it's a future. So you cannot get access its value, but you can get access the tensor shape. And because most of them don't depend on the value of the tensor, it only depends on the shape of the tensor. So all the schedule code can run all the same code as before. They can run, but when you want to access the value of the tokens, you can use the future get the real result. Yeah, only when the GPU worker and prefix matching need. So for the GPU work, it's okay. Yeah. And the last challenge is the Python GRL. I think we have finished the job for the first challenge and for the second challenge. But for the last challenge, we are a work in progress. There are some ideas. For example, in Python 3.13, it can remove GRL. Maybe you can try it. But I think some user maybe cannot use Python. The latest Python, maybe they use Python from 3.9 to 3.12. So we also have another idea too. We can use multiple process, but need to make the serialization very fast. I think it's also work in progress, and we have to do some validation for that. So yeah, maybe if you are interested, maybe you can join our Slack to discuss about the details. And currently, it's still a single thread, but we use the free CPU circles after CUDA graph launch. Okay. And the next steps, we can do some things. Maybe we can try Python 3.13 without GRL. We can also implement a multiple process version, and we can also try some faster HTTP server. Yeah, because recently Brian also do some Rust related work. Maybe after that we will introduce a Rust-based HTTP server to replace the current Python based HTTP server. Yeah, and I think after we doing all of this, we expect about 10 to 20 base performance improvements across all workloads in the next big release. And we do some simple benchmark, but I think, because recently we want to release a new blog for that, and I think more detailed benchmark results across various scenarios will be released. So please stay tuned. Okay, let's get step to the second part. The second part is about the FlashInfer optimization. Actually, SGLang has integrated FlashInfer as its default backend since version 0.2. And right now, FlashInfer also do some optimization, but it has not been released yet. Let's explore the upcoming optimization that FlashInfer plans to introduce. Because we collaborate with Flash team very closely, so we can get access the latest code, and we do some conduct some integration and performance benchmarking in advance. So here we introduce this. First, I want to introduce the FlashInfer. What is FlashInfer? FlashInfer is a library for LLM. It provides a high-performance implementation for some LLM GPU kernels, such as the attention kernel, sampling kernel, normalization kernel, and activation kernels. I think it's widely used. It's used by SGLang, by VLM, by TGI, and MLC engine. I think all of the open source framework adopt FlashInfer as its backend, and in SGLang we use it as the default backend. And yeah, because a specialized presentation on FlashInfer is expected to shared by the creator Zhang in January next year in GPU mode. So I will only have a glance of that technical optimization. Yeah. In the upcoming new release FlashInfer, it introduces mainly 3 optimizations. The first one maybe it's not optimization. I think it's used for more customizable and for the usability. It's inspired by flex attention, and it designed a customizable CUDA template and a GIT compiler that can take the attention variant specification as input and generates the optimized kernel code, such as it can generate a CUDA code, it can generate the Catalyst code. In the main branch, it supports it already. It supports GIT, and it also keeps the AOT because some framework also want to use the AOT version, and it has not released a new version yet. We also publish a paper for that, but right now it has not been public, so I will not talk more details about that. And also we do some attention work, some Flash Attention 3. The original Flash Attention 3 doesn't support the paged KV cache, but I think paged KV cache is very important for ARM serving. So FlashInfer supports it and introduced the support for paged KV cache. This part implementation is also ready, but right now it has not been made public yet, and I think it's expected to land in soon. The last one is the okay.
Yineng, I just had a quick question. So I'm curious, I've heard this is like a very shallow question today, but like I've heard that like SGLang is better because it doesn't use page attention, it uses like radix attention. I was wondering if you could give us like a 2-line summary of the trade-offs and why and why SGLang is now choosing to support both regimes.
Okay. Of course. Yeah. I think SGLang chose use the radix attention. So that means it's also paged attention, I think, but the block size is 1. And for other implementations such as VLM, mdeploy, and other framework, the block size is maybe 32 or maybe 16. I think for SGLang, it used the radix attention. It used the block size 1 just for the better for the prefix cache match. It used the size 1. It can match most of the shared prefix cache than other sites. I think that's the reason why we chose the size 1. And I think the performance, you say, if we enable the prefix cache, I think the performance maybe SGLang is better than others. And if we disable the prefix cache optimization, we compare the performance, such as compare SGLang with VLM. I think it's also compatible. Competitive. Its performance is also good. So I think we chose token attention. We use the size 1 just for better prefix cache sharing, and it didn't introduce any any other drawbacks, so we use it.
I think it's not just the prefix caching, it's about the tokens, how you actually get even in your user query. So that was one main reason why radix attention was so good in caching your KV states across multiple queries. If you're doing a batch size, right? If you're doing a batch size of 1 inference, then it does not matter whether you use VLLM or page attention or any of or SGLang. Fundamentally, it is identical. But if you have a number of batches and if you're serving them, then you would rather prefer to not to do the recomputation for those queries or for those tokens that you have already computed. You would rather prefer to reuse those and increase your time for your first token or even time between tokens too.
Right. That's also a reason. Okay. Thank you. Thank you for your advice. Okay. Maybe let's get the next slide. Okay. Yeah. Yeah. So next slide is the StreamK scheduler. I think, yeah. Actually, this job has been open sourced, but right now it has some conflicts, and yeah, I just tested this, and its performance is better than I thought. What does this do? Yeah, it is inspired by StreamK, and to minimize the idle time of SMs by distributed the workload. So I think for some scenery, such as one scenery, we use some random input, and the random input length is distributed from 500 to 2000. Yeah. So the input length, some input length is long, some input length is short. And in this case, yeah, if we don't do any scheduler optimization for that, I think, yeah, the performance is not very good. And what does the scheduler do? It cannot affected by the variance of the input length. It's only related with the total length of the input length. And yeah, so this algorithm also I think is published as in the paper. And the idea is that it takes the sequence length information of the query of the output and the key value dimension as input, and the output mapping between work and the CTAs. So the index mapping between partial and final outputs. Yeah. I think maybe yeah, maybe if you're interested, you can refer to this PR. Yeah. Okay. And here is the results. Yeah, we compare the new FlashInfer with the Triton implementation. And here is two scenery. One is the Share GPT scenery. We just use 1000 promotes for that. And we use the request rate, I remember maybe 46. Why we use that? Because we just want to test the online scenery. We are latency sensitive. Maybe we use the TTFT 200 milliseconds for the threshold. And another scenery is the random scenery. As I said, the input length is ranging from 500 to 2000. And for this case, its input length is variance. Yeah. And yeah, for these two scenarios, you can see that the FlashInfer backend, yeah, its performance is better than the Triton backend. Just for the TTFT, for the ITL, both good at. Also, I think its performance is very competitive, even with some other not fully open source framework. But what I do, my work primarily focus on the integration and do some validation for the upcoming FlashInfer new version with SGLang. And yeah, for the benchmark job. If you have more questions, maybe we can just join the Flash Slack channel. I and Zhao also in the channel. We can have more discussion about that offline. And yeah, the last thing is the TurboMind GEMM optimization. Right now, SGLang depends on some VRM component. We just use VRM for the linear component, such as some quantization method, AWQ, GPTQ, and W8A8. And we want to remove the VRM dependency, so we need a high performance quantization implementation. Yeah, TouchAO team, Jerry Zhang also sent some PR for that, and thank you very much. And we also want to integrate the TurboMind GEMM implementation. I think its performance is so good, and here I will share some technical details about why its performance is impressive. First, let me introduce the TurboMind. LM Deploy is a toolkit for compressing, deploying, and serving LMs. It's developed by Shanghai AI Lab. I think the initial release is last year at July. It was built upon a modification version of fast transformer, and after subsequent iteration, right now, yeah, it completely rewrites the attention and request scheduling logic. So its performance is so good. And the TurboMind is TurboMind is specialized in the GEMM optimization component. And it's original a part of ARM deploy, but right now it has been extracted to release as an open source library. So I think in this way, other frameworks such as SGLang, FlashInfer, or TGI can integrate it as needed. It primarily focuses on accelerating linear operations, including the quantization and the MOE. Yeah, here is the link. Maybe you can give him a star. And yeah, what TurboMind GEMM, what is the problem TurboMind GEMM solve? Yeah, I think the GEMM operand in the tensor core area is the practical. This is the workflow. First, it will load the operand from the global memory to shared memory. And the second, it will load matrix fragments from the shared memory to register. And the third part, it will feed the tensor core MMA instructions with the fragments. Step 2 use the some instructions such as LDSM to effectively transform the column major or row major layout to the layouts required by MMA instruction. However, when the operand bit width is different from tensor core's input bit width, such as we use int4 or int8 vs float 16, the loaded data will be misaligned because the instruction is not designed for to handle such mapping. Yeah, I can share with you some PTX ISA. We can use MMAM16 and 8K16 as an example. Here is the picture to draw the idea. You can see that here is thread 0, thread 1, thread 2, thread 4. For thread 0, it handles this one 0, 1, 8, 9. And I think this is for the float 16 case. And if it's for 8 int 8 case, the thread 0 will handle 0, 1, 2, 3. And that will make this misaligned, and the result will be wrong. So in order to use it, we do some I think other GEMM implementation optimization, they designed some layout to match the tensor core's layout. But you know, tensor core, there are so many tensor core layout, and in different architecture, such as in Phi100, in A100, and in H100, the layout is also different. So I think it's not maintainable and it's not a general approach. But TurboMind GEMM proposed a method that can generate and elegantly resolve this problem. What does it do? It just do the packing the weights. Instead of designing complex weight layouts to make the quantized weights compatible to specific tensor core instructions, we reuse the vendor provided instructions like LDSM. What does it do? Here is the standard GEMM, and here is the weight packing. This is offline, and here is the mixed precision GEMM. First, we do some bit extend, such as the 4-bit weight to the 16-bit, and we load the weight fragments with the same data pipeline as in the standard GEMM. You can see that this one load from the GEMM float 16 from global memory to shared memory, and from shared memory to register. This code is the same for the standard GEMM, or for the weight packing is the same. And the bit unextended 16-bit data to 4-bit here with additional reordering. Here is the pack and the store. And after that, this is the offline instruction. After the offline, we use it for the online mixed precision GEMM. Here is the int4 packed, and it load into the shared memory. We can just use LDS. We don't need to use LDS matrix. For the int4 register memory, and we can use this. And each warp stores the packed fragment back to GEMM. And sorry, this is some typo. I will fix it. And here we can use an example. You can see that here is 32 multiple 32 matrix can be filled as 2 multi 2, 16 multi 16 slice. Each 16 slice, is a stride just for this blue area. I think it's not contiguous. Yeah, it has some stride. This is a stride. And tail is then packed into a contiguous 32 multiple 8 tail. So 2D packed shape is 2, and this is 2. And this is 32 multiple 8, and this is 2 multiple 32 multiple 8. So this is 512. The transformation that maps the original MN coordinate to the packed shape is M divided 16 and N multiple 16. Yeah, this is an example to use this tensor core instruction. And yeah, what's the advantages of this TurboMind GEMM? I think it can save the layout directory maps to tensor core instruction, and it's more general. Yeah, you can use it on A100, you can use it on H100, even on the Blackwell, you can use it. And it can be loaded natively without bank conflicts, or it's Switzerland free. I think in Catalyst, there are also some solution for the mixed GEMM. Yeah, but I think this way is so elegant. And it can adapt to any layout required by MMA instructions, even undefined. It can adapt to any power of 2-bit width, and the number of fragments to pack is configurable. And okay, here is the benchmark result. We can just use a float 16 multiple int 4. Yeah, the group size is 128. Here, how the 4.25 compute? Yeah, because the group size is 128, and yeah, we can use this. Use the 4 multiple. This is 512. Yeah, and because we save the scale and 0 in 16, so plus 16 and plus 16 is 544. 544, yeah, divides the 4. Divides the 128. So the result is 4.25. And yeah, it can compare with the float 16 with the cuBLAS implementation. And we can see that, yeah, here is the batch size, and here is the speed up compared with cuBLAS. I think these lines with dot is for this, and these lines is for these T flops. And we can see from the chart, yeah, when the batch size is less than 256, most of this is even faster than cuBLAS. Yeah.
So
Okay.
so Yineng, I'm curious at the chart, like it looks like your performance numbers on older GPUs are like insane. It's like close to 4x, versus on H100 it's like much slower, like close to 2.5x at the small batch size. So I'm sort of curious if you could speak more to what's going on here.
Yeah, you're right. I think the reason why is because you know, in China, I think NVIDIA yeah, for some restrictions, it cannot sell some H100 or some, yes, even the A100. So I think the optimization is mainly targeted on some V100, A100. It not even use the H100's new features. And I think after this release, the TurboMind GEMM's author Zhang, he's also in the meeting right now. He will do some optimization for the new architecture for H100. Yeah.
Very interesting. And so related, Wu Hyung is asking, like, why does the batch size increase? It's slower than cuBLAS. Is it because of the lack of tensor cores?
Oh, why is it okay? Yeah. Good question. I think why is it slower in large batch size? Yeah, in large batch size, plus implementation is so good. Maybe Zhang can can answer this question? Actually,
well,
I'm not very sure about this.
For now, skill issue then, it seems like. Okay.
Okay.
Very cool.
Yeah, that's a good question. Yeah, we should figure out. Okay. Yeah. That's all. And the last is some community users and contributors, such as XAI, AMD, PyTorch, NVIDIA. Yeah, XAI, I think they use it. Maybe they do some internal version. AMD give us some support to run it on AMD. PyTorch, yeah, TouchAI team also, yeah, use the integrate TouchAI into SGLang. I think it's so nice. And NVIDIA support us with some cloud credits. Databricks, I think it's used for the research purpose. And Rumpod also give us some credits. BattleDance, the Singapore team, Lava One Vision, use SGLang as the default LLM inference engine. Yeah, and LinkedIn, maybe Brian can say about it. Also, we collaborate with so many companies. Okay, one more thing. Yeah, we have the Slack channel, and we also have some bi-weekly development meeting. If you are interested, you can join our channel, and you can also, yeah, open this link. This is the SGL community meeting. You can post your ideas in the doc and discuss with us, with the developers. Also, we support the Jupyter Notebook documentation. I think it's so cool. We have summarize of the learning materials. You can open this link. Yeah, you can see that we have the summarize for the blog slides, for the videos, and for the paper, for the documentation. Also, we public our development roadmap. This is for you can see this for details. And I think something need to be highlighted. We will support speculative decoding in this quarter, and we will do some long context optimization. I think right now, yeah, you know, for some even for Llama, I think its context length is from 4K to 32K. Even right now for the 128K. So I think long context optimization is necessary. We also do some exploration for the disaggregate preview and decoding. I think, yeah, for the online scenery, TTFT and ITL is very important, and the disaggregation is a good solution for that. Also, it's a little complicated, and I think other frameworks such as VIM and, yeah, maybe other frameworks also right now, yeah, maybe do some investigation or want to implement this. That's all, yeah. And yeah, do you have any questions?
Very cool. Thank you, Yineng. This is an awesome talk. I guess like, yeah, if anyone has any questions to Yineng, please start posting them in the chat. Like in the meantime, I want to ask, like, maybe I'll start. It's like like I was actually really impressed by like how quickly of a community the SGLang team developed and the like volume of people that you've been working with. So I'm curious, like, if you have any suggestions for people that are interested in the project, that want to learn more about LLM inference perf, like where should they start? What kinds of issues should they target? Who should they talk to, etc.
Yeah. Actually, we welcome the new user. We will also welcome the developer. We welcome anyone interested in this project. I think, yeah, if anyone is interested in this project, he can join our Slack. He can just use it, and if he encounter any issues, any problems, he can, yeah, raise an issue. And if he want to do some modification, he can read the code. He can, yeah, just add that feature and send a PR. We are willing to review that. And I think, yeah, right now we have 3 code developers, and we will handle these issues or PRs quickly. And yeah, I think right now there are so many LM inference frameworks. So maybe for the performance, TensorRT LM is good, but its usability is not good actually. For the customizable, if you want to do some secondary development, SGLang is very suitable. Yeah. And I think, yeah, anyone who is interested in SGLang can join us, join the Slack, and we can have more discussion, anything for the technical details for the just as a usage, yeah, we have that. That's all.
All right, yeah, I see some questions from Amgad. Any plans to add other transformer types? Example, BERT and Whisper?
Yeah, right now, actually, right now we don't support the Whisper, and as far as I know, yeah, if you want to run Whisper so fast, I recommend you use TensorRT-M. Yeah, its runtime maybe at this time point is the fastest among all of the implementation. Yeah.
A question I had, I think it's on the previous slide, like the first bullet point. Could you like break down slightly slower? I think it's the slide before this.
Okay.
I just,
yeah.
oh,
Yeah, go ahead.
I always get confused what people mean by partial bits. It said like 4.25 actual bits.
Phil, it is the effective bit that you have to consider when you think of doing the alignment for your data. So let's say that you want to represent your memory representation in FP16 multiplied by int4. You need to consider what your layout strategy should be for doing the memory allocation and also memory managing when you do the pull of the data. You have to keep some part of your data for your actual mantissa and some part of your data for your exponents, right? So how do you bring that data effectively is the fundamental question. And the fact that we have 512 bits for the mantissa part and the remaining for doing the scaling and scale out part of the data field, you need somewhere around 544 bits to represent the actual data in the memory. Now, if you want to bring in a group of that, then you need to divide by 128. So you end up getting 4.25 actual bits to pull that data. Now, that gives you like like from the view of like how do you look into the data, you have more bits representing a data value. Hope that clarifies.
It does. Thank
I'm
you.
giving you like a 10,000 feet answer here.
Thanks.
Nice
And
exploration. Thank you.
Yineng, I may be wrong, so correct me. Okay, so.
Okay, yeah. You're right. Yeah, because we store the 0 and the scale in 16. Yeah, I think I can write that. Yeah, maybe wait for a moment. I think it's easy. This one, I just posted this in the chat history. Oh, any other questions?
I see one from Byron. Any thoughts about SSM models?
Oh, SM models. Yeah. Yeah. I think maybe Ying can answer this question.
Yeah, I also tag in.
Yeah. Maybe we can give some permission for Ying to unmute the
yeah.
microphone.
Okay. I just did.
They might be away from their keyboard. I just noticed. I think anyone can unmute themselves. So.
Ying, are you around? You can unmute yourself.
Oh, okay. Yeah. Okay. Yeah, Ying has replied this. We are definitely open to support it. Yeah. It's not our first priority. Welcome contribution.
All right, very cool. I guess if you're interested in like reaching out more to Yineng, like I think you already mentioned like a bunch of like different like Slack channels where you can participate. And he's also on Twitter, so feel free to reach out to him there. next week we're gonna have Jay Shah, who's gonna be talking. He's one of the co-authors of Flash Attention 3, and he's gonna be talking to us about like just exactly that. He also has a really nice blog called Colfax Research that I really highly recommend you check out. So yeah, see everyone next week, and thank you everyone.
Yeah. And yeah, after this meeting, I will share my slides with Mark, and maybe, yeah. Thank you.
Thank you so much. This is really good. Thank you. See
Thank
everyone.
you. Bye-bye.